So viewers, welcome back. We were talking about classification algorithms, right? Now we would start talking about the types of classification which are possible. It can be the binary classification, it can be the multi-classification, right? Now the binary classification where we have only two choices, like for example loan, approve or reject, email, spam or not spam, right? Exam, pass or fail. So specifically I am talking about two classes. So binary classification is just like a kind of verdict, right? On the other hand, the multi-classification, you may have more than two options or more than two classes, right? For example, disease types, so there can be multiple disease types. The product category, again there can be multiple product category. Language detection, there can be multiple languages that you are trying to detect, right? So multi-classification is like choosing the correct department in a hospital, for example, right? Or for example, finding the correct product type, for example. For example, as you can see in the diagram, I have shown the binary classification, I have shown the multi-classification example, right. On the left hand side, you have only two classes, for example, right. On the right hand side, I have three possible classes that I am talking about. I have donated those classes with suppose 1, 0, 2. On the left hand side, I have just donated them with suppose two numbers 1 or 0. We normally call it as binary, right. Similarly, as you can see in this particular example, which is iris, it is a very popular data set where you have three classes, right. What kind of flower it could be? It belongs to the categories. So, it is an example, a perfect case of a multi-classification problem. Similarly, over here as you can see, you have multi-classification, classification of the vertebrates, for example, right. So, the brain of classification exactly is the decision boundaries where I talked in the previous session. So, classification model is actually constantly asking you where should I draw that line, that decision boundary I was talking about, so that the mistakes can be made minimal, right. That is the bottom line about the entire classification problem, right. Examples could be, for example, college admissions, marks, you may have marks, you have entrance score, you have interview performance, for example. So, there is no perfect, for example, cutoff in this case, it is just like a line that feels fair overall, right. So, we look for that particular line. So, classification is not about certainty, it is all about the best possible separation between the two or the multiple classes that we have, right. So, you are drawing a line, on one side of the line you have another class of data, on the other side of the line you have another set of class data, right. As I can show you over in this particular examples. So, on the left hand side, as you can see, you have a line which has a linear line which separates the two kind of data, right. On the middle case, you can see above, like it is not always possible to separate the two different classes by a linear line. We would talk about in possibly in the next session that what exactly needs to be done, because I told you that at times linear line would not be enough, you might have to draw a curve, right. So, we would call it that single line would not work, right. On the right hand side example also you can see that even the curve could be more complex in that case, right. Similarly, as you can see in the below cases also, where you can see that there can be you have to draw multiple lines, for example, to classify multiple classes, right. So, it is all about drawing that decision boundary, and this decision boundary cannot be drawn in a single iteration. You might have to do a lot of iterations actually to bring back or to draw this particular decision line properly, right, which can actually separate so data quite well. So, that is the overall possibilities. Let us talk about the probabilities. Where does the probabilities actually come into before actually decisions, right. So, the most classification do not think yes or no, right, rather, although we told that the classification we always talk in terms of the classes, right, but actually when we talk about the mathematics, they actually would not talk in terms of yes or no, it does not know, algorithm does not know about it, right. They actually think in terms of something called confidence, yeah, that word confidence is more important. For example, there are 80% chances that this transaction is a fraud. So, in that case system applies a threshold, right. So, above 80% for example, I would block, say suppose below 80% I would allow. This could be a threshold which would be draw by or would be established by a programmer or a person, right. So, decision comes after the confidence, right. So, that threshold actually allowed me to put both the things into two classes, maybe block or allow, right. But ultimately it was the threshold, right. It was the confidence which could be expressed in terms of probabilities, for example, right. So, decision comes after the confidence which was given. So, classification algorithms, I would first take something called which is a very popular algorithm called logistic regression. We will try to understand what logistic regression is all about, and we will try to see what are the basics about logistic regression. So, logistic regression is a very simple but yet very powerful classification algorithm that thinks in terms of probabilities, right. It looks at inputs, it produces a confidence score, right. It would convert then it into a decision, right. So, logistic regression is not guessing, it is about weighting the evidence, I would say, right. So, how machines learn to say how confident am I. So, if I say a patient has 70% chance of having a disease, for example, right. So, have I made a prediction in that case or a decision? So, actually neither. So, I have actually expressed the uncertainty, to be very frank, right. So, logistic regression exists to model the uncertainty first and then make the decision, boundaries or decisions, right. So, it is the uncertainty which is an important turn over here. So, why a linear regression would fail for decisions, for example, let us come to that point as well. So, linear regressions might say, for example, probability, actually they does not talk about the probability, they talk about a continuous value. So, there might be a value 1.3, they might throw a value suppose minus 0.4, for example. So, does a 130% disease probability would make a sense over here if it says 1.3? No, not at all, right. So, we need a model that is disciplined, right, one that never gives you a value beyond 0 and 1, so that I can express it in terms of confidence or in terms of which is nothing but a probability, right. So, the limitation gives birth to, I would call, logistic regression, right. So, logistic regression guarantees that one thing for sure, that every prediction will lie between a value of 0 and 1, right, which would be a representative of its confidence level. So, logistic regression does not think in probabilities initially, to be very frank, right. Instead, actually it does what? It first computes a raw score, right, and this score can be positive, negative or any large, small, whatever, and then this score represents how strongly the evidence learns, right. For example, now imagine suppose you have a smooth decision gate, for example, right. So, the strong negative score, for example, you can associate with a confidence close to suppose 0. The strong positive score you can associate with a confidence close to suppose 1, and net 0 you can be uncertain, you can attach uncertainty around it. So, this gate actually mathematically is implemented using a function which I would call sigmoid, right. So, sigmoid actually converts this belief into probability, right. So, logistic regression actually does not decide by itself. So, it outputs a probability first, then humans decide, or the programmers decide, or the person for whom you are solving a problem, who knows about it, they decide that particular threshold. It can be suppose 0.5, 0.7, 0.8 depending on the problem type, right. So, for example, in fraud detection, I could set it to say suppose 50%. So, I may say that too risky, block many genuine users, it could be 95%, I would say safer, but it misses out some kind of fraud, some fraud obviously. So, that deciding that threshold is something which lies with the hand of the programmer or the person. So, in this case, so linear logistic regression learns by I would say punishing the confident mistake more harshly, right. Example, like for example, predicting 51% wrong. So, I can provide a small penalty, predicting 99% wrong, I would give a huge penalty, I would apply a huge penalty on it. So, the model is trained to be humble when uncertain and bold only when the evidence is strong. So, this is the concept behind the something called log loss. I will not go into the mathematics too much, but this is what the simplest way you can understand log loss. So, we would talk about logistic regression in terms of the feature weights also, that is also important to understand. So, each feature would get a role or a vote, I would say, right. So, positive weight, I mean you can it might represent that it pushes the decision boundary to class 1, for example, right. A negative weight, you would say that it pushes the decision boundary away from it. A larger magnitude may represent a stronger influence. In medical domain examples, say suppose a person who has a smoking history, right. The strong positive push can be given in that particular cases. A regular exercise person who does it, it requires a negative push or no push at all, right. So, I mean logistic regression is a weighted, I would say, debate among the features. So, importance of features is associated with the weight, right. So, I mean someone might ask you why you have using the word regression. Ultimately it is a classification algorithm, but regression word is very confusing, right, but still we call it a regression, right, which actually gives me a thought process that it is associated with a value. So, it is called regression because it learns the weights like a linear regression, right. So, output is the probability and decision is a classification. So, yes, I can understand that name is historical, but not very logical, but yes, that is how we study logistic regression. Now, where this logistic regression would apply and would be great? So, when the question is how risky is this, risk modeling can be one example. Like logistic regression is not you can say is not obsessed with the predictions, it is obsessed with the risk. Like the bank would never ask you, they do not ask like will this person default, they would rather ask what is the probability of default of this person, right. Similarly, it can be the medical trials, for example, where we talk about limited patient data, we talk about high cost of errors, we talk about need which requires stable behavior. So, logistic regression I mean does not overreact, right, they does not hallucinate these patterns, they generalizes better with these small data sets. So, when the data is precious, no, the simple models behave better, although I mean logistic regression is always considered to be very simple and very powerful, I told you. Similarly, when you need a stable and predictable behavior, that is where you would start talking about logistic regression, right? It would be more useful. For example, spam filtering. So, sudden spikes may cause distrust, right? You need consistent thresholds, for example. Logistic regression in that case will produce a smooth probability changes, right. It responds gradually to evidence. So, though no sudden mood swings is there when we talk about regression, logistic regression. So, that is again a scenario where logistic regression might do quite well. Similarly, when the business policy must control the decisions, obviously. So, this is a high technical and impressive example. For example, I would say that logistic regression separates the model intelligence from the business policy. So, model outputs the probability and the business sets the threshold. So, I told you that it is the threshold that matters. So, here the business owners, the one who wants to set that threshold can actually decide how the classification would be done. So, they are actually guiding the classification, right, once you see the output probability, right. So, it can be insurance case. So, low risk auto approval or medium risk or a manual review, right? For high risk it can be a case of reject. So, the same model, multiple decision layers can be there. So, this flexibility is very rare among even the complex models, and that is the reason why why logistic regression is still so popular, right. Even when the features effects must be interpretable. No? So, logistic regression lets you know, lets you see how each feature pushes the decision boundaries, right. So, that is again one of the reasons why logistic regression is so popular. So, there can be many examples like where the loss segregations takes is quite important. You can always figure out many such cases, right. So, when the speed and the scalability matters, again that is a case where the loss segregation is again very important. It is very fast, right, in terms of training, in terms of the prediction, right. It can do the real time fraud detection, online and the click predictions, large scale recommendations filtering, low computational cost, it is easy to deploy, it is easy to monitor as well. So, a lot of advantages are there when we talk about loss segregation. Similarly, when you need a strong baseline model, that is also a place where loss segregation might fit in very well. If loss segregation performs well, the patterns might already be solved, for example, right. So, there are also need to talk about the performance metrics for regression classification. So, how do we know that which model actually does good, right. So, whether this model is good or bad, right. A model is useless unless we know how wrong that it is, right. So, performance metrics exist because accuracy alone is not sufficient, right. So, example, in case of regression metrics, if we talk about regression. So, in regression we are not asking right or wrong, right. We are asking rather how far off we are actually. So, all the regression models are the variations of error measurements. So, when you would talk about the metrics about the regression, it would be centric towards the errors, right. If I talk about some of the metrics like absolute error, we call it means absolute error. So, suppose I predict the house prices. So, sometimes I am 1 lakh off from the actual, right, and sometimes I may be 5 lakhs off, right. So, it would ask, this metric would ask, on average how wrong am I, so ignoring the directions. So, why it is powerful? Because it is easy to interpret, it is the same until as the target, right. So, it tells you the typical mistakes you make, that is the concept about MAE. Similarly, there is a metric, very popular metric, which is called squared error, right, where we talk about either the MSE, right, or we talk about the RMSE, that is root mean square errors, which actually talks about punishing the big mistakes, right. So, some mistakes are more dangerous than the others. For example, predicting rupees 51 lakh instead of 50 lakh, okay, right, it is not such a issue. Like for example, predicting 10 lakhs instead of 50 lakhs, it can be a huge mistake, right. So, the square errors, and it actually punish the big mistakes more by taking the square term. So, it exaggerates the large errors, and when we talk about root mean square, it actually brings back to the original limits, right. So, they actually screams when the model makes big mistakes. So, that is the overall context behind your root mean square and the mean square error. Similarly, there is another very popular metric which we call it as R square, right. So, R square actually does not tell you that how accurate the model is. If I do nothing smart at all, for example, what is the laziest prediction I can make? That is the question it actually focuses on. So, you actually predict the average every single time when we talk about R square. So, R square simply asks you how much better is my model compared to the laziest average guess that I have made before. So, if in case R square is equal to 0, it is useless actually. If it is 1 or close to 1, it is in fact 1, it is considered to be perfect, or close to 1 would be a good case, and if it is less than 0, it is absolutely embarrassing. So, the values close to 1 are considered to be better cases, right. R square actually measures is a learning actually, it is not an error, right. So, R square of suppose 0.8 for example. So, it would explain that 80% of what going on, right. That is the key concept that you must remember. So, remaining 20% is a noise or maybe unknown factor which is beyond your control. So, I mean this 80% would be considered quite good when it comes to R square. So, why accuracy is dangerous alone if we talk about? So, accuracy is the most popular, I am talking now about the classification metrics, right. So, the accuracy is considered to be one of the very popular metrics when I talk about classification, but mere accuracy is dangerous, right? That is what I am talking about. So, accuracy is the most popular term, and in terms of metrics when I talk about classification, and it is also quite misleading metric, right? For example, 99% emails are not spam, yeah? And the model predicts not spam always, right? So, accuracy over here is 99%, but the model would be absolutely useless in this case, right? So, that is the reason I was talking about that it can be misleading as well. So, the accuracy hides the minority mistakes, very minor mistakes as well, right. So, every classification outcome falls into one of the 4 buckets, I would say, right. So, it would be the correct positives, it could be the correct negative, it could be the false alarm, it could be the missed detection, right. So, all the classification metrics are not are just different ways of looking at these 4 numbers, right. That is one of the most important metric when we talk about classification. So, I would talk about certain metrics called precision versus recall, for example. So, precision is what? Can I trust you, right? So, when the model says yes, how often it is correct? I will take an example, spam filter blocking the genuine emails. So, it is a bad precision, right? So, precision matters when the false alarms are costly, yeah. Similarly, when you talk about recall term, so did you miss anything? So, that is the tagline that you must remember. So, out of the real yes cases, how many did you catch? That is what in a way you can remember recall. For example, it can be missing the cancer patients. Obviously, it is not acceptable at all in any case of the scenarios, right. So, recall matters when missing is dangerous. I hope you understood the difference between recall and the previous case that we talked about precision, right. So, I mean the precision and recall trade off, this is a very famous term that you would be able to find when you learn machine learning, it is a very important trade off. So, can increase the precision or recall, but rarely both can be increased at the same time, right. So, in case you have a lower threshold, you catch more positives, it is a case of high recall, right. More false alarms, it is a case of low precision, right. So, higher threshold, it can be the fear false alarms, which is again a case of a false high precision, and similarly more mistakes, it is a case of low recall. So, this is not a technical issue at all, it is a policy decision rather, right. Similarly, I mean there is very popular metric which is we call it as a F1 score, which actually mixes up both the cases, right. So, it is compromise, it is actually compromise between what? It balances your precision and recall actually, right. So, it is useful when classes are imbalanced, right. So, F1 asks you, are you consistent, reasonable or not? There is another term called AUC-ROC curve, which is again very popular metric for classification. So, instead of actually asking, is this prediction correct? AUC-ROC would always ask a smarter question. Can the model tell good cases from the bad cases better than the random guessing, right. So, that is the tagline that you must, or you can raise this question in order to understand it. So, AUC over here measures how well the model separates the classes across all the thresholds. You can set, say, suppose 0.5, it can be a random guessing, it can be 1.0, which is actually a perfect separation. So, AUC actually evaluates the ranking ability of a classifier, right. So, that is it for today's session. So, in the next session we would talk about other machine learning algorithms, other supervised machine learning algorithms, and in the near future we would also talk about unsupervised machine learning algorithm. Thank you everyone.